welcome. So, in the previous lecture what we talked about that there are different types of breakup, vibrational, back type, multimode. Out of that we pick up a more simpler of the breakup models, and it is basically vibrational breakup, and this comes from the Taylor analogy breakup model. Okay. The courtesy to Aruke and Amsden is a 1987 paper where they first actually did it. Now, as I said that the vibrational breakup is like a single degree of freedom system. So, what Aruke and Amsden did was that they compared this oscillating droplet like this, right, this oscillating droplet and distorting droplet also with a spring mass system like what we have shown over here. It is like a spring mass system. This is the damper, this is the spring, and this is whatever is the forcing. Now, that forcing here in this case is aerodynamic forcing, right. The predicts when the aerodynamically disturbed droplet is likely to undergo breakup, right. So, that is the whole objective, and it uses the droplet level information. It is very useful in the secondary atomization in the Weber number range that we said 11 to 2, right, in that particular range it is particularly useful. Okay. So, what was the equation of Aruke and Amsden, right? What kind of an equation did they actually write? So, they wrote the equation for a simple damped harmonic oscillator, that means harmonic oscillator with a damping, right. So, they were kind of ingenious, and so the harmonic oscillator's equation is this, right. So, this is the forcing function. Okay. This is basically what we call the spring constant or the restoring force. Okay. This is the damping component. So, the spring restoring force here, okay, is by common sense it dictates it has to be surface tension, right, surface tension. Okay. Then external force is the aerodynamic force, and the damping force is nothing but the viscous force. We missed a u there. Okay. So, damping force is nothing but the viscous force, right. So, based on this equation, okay, basically it says that this is a spring mass system which has got surface tension as the restoring force, damping viscosity as the damping force, and aerodynamic force as the forcing function. Okay. Now, if you try to write it, so write it in this particular form, then you will find that this is the equation that we the individual terms will be like this. Now, in this individual terms, if you look at it carefully, okay, what is Ks by m? Ks by m root over is usually given as the natural frequency of the system, right. So, this term over here is nothing but omega n square, so to say. This is the natural frequency of the system, as you know from your vibration, that is given by root over Ks by m, right. Okay. Similarly, d by m, that is given by that damping, okay, and f by m is basically the forcing. Now, as you see, we have carefully chosen our units over here. This is sigma divided by rho l r cube. This is given by mu l, because this is viscosity dependent, divided by rho l r square, and forcing of course involves that rho g, because it is aerodynamic forcing, okay, and this is u squared is nothing, u is the relative velocity. In case you have not guessed it already, it is the relative velocity, okay, u, and mu l is basically the fluid viscosity. R that you see over here, R is the undisturbed droplet radius. There is no evaporation here, okay. This is the undisturbed droplet radius, okay. So, these are the quantities that you will have over here, got it, okay. So, what is x now? Now that we have said that this is a spring mass system, x is nothing but, if you look at this particular picture over here, let me draw it a little bigger, right. So, it is basically the displacement of the droplet equator, okay. It is the displacement of the droplet equator. So, this is basically your x, right. It is the displacement of the droplet equator, okay. So, based on an aerodynamic load. So, the aerodynamic force is coming this way, right. So, that is the displacement of the droplet equator, Okay. So, when this displacement becomes very high, right, what would happen? What would happen when the displacement becomes very high? The droplet will undergo the breakup, okay, and we will see when it undergoes actually breakup. Now, there are few other things that you see. There is something like CF, CK, CD, these are all constants about which we do not have an idea over here. This requires experiments and other things, okay, to fill in, to plug in those constants, okay, because we do not have an idea that what those constant values will be, right. Okay. Now, the breakup condition happens if the north and the south pole of the droplets meets at the droplet center, right, and since it is a single degree of freedom kind of a system, say you consider this particular case. So, this is the original droplet, right, and this is the droplet at the point of breakup, drawn it like this, forgive the drawing part. So, this is x, this is the deformation of the undisturbed droplet equator, right. So, this x, if you look at the deformation, this is exactly half of the droplet size, right. So, when x is basically half of the droplet size, right, it is supposed to undergo breakup, right, because then when the north pole and the south, this is north, this is south, this north pole and south poles actually meet, and the deformation extent, that is the deformation of the equator of the droplet, that becomes equal to the droplet diameter or the radius of the droplet in this particular case. Okay. So, what we can say over here is that you can define a quantity which is called y equal to x into Cb by r, Cb is another constant. So, based on that, when Cb's value is equal to half, the droplet actually is said to have undergone the breakup. Okay. So, substitution. So, now what we do is that, so you know all these parameters now. Now, let us get away from this and write the equation in the journal thing. So, when you put all these things, so Cb is also a constant. So, using the expression d square y by dt square now becomes Cb, Cf by Cb, rho g by rho L, u squared, u remember was the relative velocity, minus Ck sigma divided by rho L r cube into y minus Cd into mu L divided by rho L into r squared dy by dt, right. That is the full equation that you have, right. So, breakup happens when y is greater than 1, right. That means, when north pole and south pole of the droplets actually meet at the droplet center, okay. And there is only one fundamental oscillation mode, right, one fundamental oscillation mode only, got it. So, that part should be very clear to all of you. Okay. Now, how to solve this particular equation, right. So, if you take this system to be under damped, okay, the basic assumption is under damped, it is not critically damped, it is not over damped. So, if you look at what is that, if you recall, if you have a generalized equation like this is a generalized free vibration equation, this is a free vibration equation, it is not forced. Okay. What you have, m should be greater than 0, b should be greater than equal to 0, k should be greater than 0. Now, the characteristic equation for this, will be ms square plus bs plus k is equal to 0. So, the characteristic roots will be, roots of this particular equation will be minus b plus minus b square minus 4 m k divided by 2 m, right. So, these are the characteristic roots of this particular equation. Now, there are three possible cases. One is when b square is less than 4 m k, this is called under damped, which is what we are dealing with here. Remember your Weber number versus Onsorge number plot, we showed that most of the systems are under damped usually. Okay. So, then 2 is basically b square is greater than 4 m k, that is over damped, okay, and 3 B square is equal to 4 mK, which is critically damped. Right. Okay. So, these are the 3 outcomes that are possible, right. We are concerned with this outcome mostly, okay, and this is from the free vibration equation, right. And but what equation that we have over here is a non-homogeneous equation, right, that is a non-homogeneous equation, right. So, this equation, the basic vibration equation that we wrote, right, usually will have 2 solutions. One will be a particular solution, right, and one will be the complementary solution, correct. Okay. So, out of that, the complementary solution will be the same as a free vibration equation. It will be equivalent to a free vibration equation minus this particular term, right. So, if you solve a free vibration equation minus this particular term, which is basically you just remove the forcing away, okay, you will get whatever is going to be the complementary solution, right. So, that is what you know from your vibrations already, okay. So, complementary solution is nothing but the same as free oscillation, okay. In this case it is underdamped, okay. So, for underdamped cases, okay, we normally there are several other parameters that we define. There is something called the critical damping, which is basically this. This is called critical damping. Then there is something called the damping ratio. Damping ratio is basically B by Cc. This is called the damping ratio. Okay. And then there is something called the damped vibration frequency. Which is given as 1 over I squared into omega n, right. Okay. Now, for underdamped system the solution becomes yt cos omega dt plus d2 sin omega dt, right. Okay. That is the main form of the equation that you are going to get, right. Okay. And this you remember is the damped vibration frequency, got it. Now, there are 2 boundary conditions that are needed to solve these 2 constants. Okay. Usually what you are given is y naught is equal to y 0, y at 0, time equal to 0, then y dot at 0, okay, this we can obviously write it as dy by dt at 0, something like that, right. Okay. So, based on that the equation becomes, and this is the same, this is the complementary equation that we are trying to find out, right, is basically omega n t into y naught cos omega dt plus dy by dt is 0, right, plus omega n y naught by omega d. This entire thing becomes associated with sin omega dt. Got it? Okay. So, that is the total expression. Got it? So, that will be the complementary solution, right. Okay. Now, in this particular problem, if we go back to our PPT now, which is over there. Okay. If we go back to our PPT here, okay, what we have done is that instead of omega d, okay, we have used omega. Okay. So, here omega and omega d are the same, okay, is the same thing, right. So, omega is actually defined over here, okay, and that is basically the damping time scale that you have, that is the damping time scale. Okay. dy 0 by dt is basically that y naught 0, right, and y 0 is the same as y 0, okay. And we have defined a critical Weber number kind of a parameter, which is nothing but the Weber number multiplied with all those constants that sits in front, right, and the Weber number is given by as rho g u square r by sigma. Got it? Based on this, we get this complete solution for the vibration of the droplet, right. As you can see, it is very similar to what we did just in the previous previous journal thing that we did, okay. And you can see that this exponential terms comes from that complementary solution that we just now saw, right, e to the power of minus, remember that, okay. So, that is what we got. So, that is basically the same as this kind of, okay. And so, you get that entire set of equation, okay, in which you get the complete solution which is equal to complementary plus particular, right. So, that is the net solution for a forced vibration kind of a system, okay. Now, another thing is that you do not see those constants C D and all those other things any longer. That is because we have substituted them with some values over here, like C B was 0.5, C K is 8, C D is 5, C F is 1/3, okay. What is the rationale behind that? Absolutely no rationale. It is basically done experiments, repeated experiments have been done, and people have found out that this could be the possible values, right. So, there is no theoretical basis for this, right. So, this basically, these values basically matches the data, as simple as that, right. So, that is how you actually have done all this thing, got it. So, that is very interesting that you now have this entire vibration problem worked out, in which you have these are the kind of solutions that we have, okay, and these are the kind of values that we have used, okay. Now, as I said, how do we find out all these constants? Say for example, one constant C K that you can see over here, which is this guy over there, right. How that is found out? Basically, it work done by lamp. You considered an inviscid spherical drop, okay, and from the frequency of oscillation of an inviscid spherical drop, one can find out what will be the value of this C K. So, C K is usually 8. So, this comes from the inviscid drop analysis, right, okay. Then people have done damped oscillation for a viscous spherical drop, right, and they have found the corresponding time scale, okay, and from there you have found out what will be the value of C D, right. So, like for example, C D then becomes 8, C D becomes 5 and C K becomes 8, right. C B we already established it has to be 0.5, right, okay. Now, there are two other constants that needs to be found out. Now, for that what happened was that people did shock tube studies. These are all experimental, and you can learn more about the experiments if you go to the individual books, okay. So, in the shock tube experiments, people found this critical Weber number to be about 6, right, okay. So, based on that, substituting that value of the Weber number, C K C V by C F is approximately equal to 2 times the critical Weber number. That gives a value of approximately 12, right. So, from there you can back out what will be the value of your C F going to be, okay, because C K and all the other things are known. So, C F is usually becomes 1/3 from this exercise, right, okay. So, that is interesting because you have planted in all these constant values. But the formalism, I think you guys are very clear. We have just taken a spring mass system, we have assumed that it breaks up at y greater than 0, and then we have found out this net solution, right. It is as simple as that, okay. And these are the constants that we have picked in and plugged in from other theoretical and experimental works, right. Now, one other thing that remains, that still remains to be done, is that what is the size of the daughter droplets. We know that it breaks up at y greater than 1, but what will be the size of the daughter droplets? As an engineer, as an experimentalist, whatever you say, it is very important that you find out what those values are going to be, right. So, it is mandated, right. So, what do you do about that? To do that, what you do is that you calculate the energy of the parent droplet. So, what is the energy of the parent droplet? It comes from two forms. One is the surface energy, okay, that is the surface energy, and the other source of energy comes from the combined action of distortion, energy due to distortion plus oscillation, got it, distortion plus oscillation, right, and K is basically the ratio of the two, the ratio of distortion and oscillation in the fundamental. Once again we are only concerned with one mode, and that is the fundamental mode, right. Okay. So, k is actually gives you a value of around 10 by 3 if you consider this. So, this is the total energy of the parent droplet. What is the total energy of the child droplet? The child droplet is assumed to be non-oscillating and non-deforming. Okay. The child droplet non-deforming means non distorting essentially. Okay. So, this particular component comes from the kinetic energy of the droplet, right, that you have, because this as it atomizes it basically spits out the droplet, right, and on the other hand this energy comes from the corresponding surface energy, right. R32 that you see over here is basically called the Sauter mean radius. Okay. There is a Sauter mean diameter, this is the Sauter mean radius, right. So, at the breakup condition, which is y equal to 1 and omega is equal to this, the resulting droplet size is given by this equation 8, where k is equal to 10 by 3 that we already mentioned. So, this is the R32. So, from this equation the number of droplets can be also calculated from the mass conservation, because the mass of the parent droplet has to be the same as the daughter droplets, right. So, that you can find out, but this will be the radius of each of the droplet. Okay. So, so these are the basic things. So, this actually tells you that what will be the energy of the child droplet, okay, and what will be the energy of the daughter droplets. Okay. Now, another thing that still remains is basically what will be the velocity of the child droplets, right. So, that is what we mentioned, velocity of child droplets. Okay. As we said earlier, this velocity of the child droplet is usually given by Cv into, these are all constants, do not worry too much about them, dy by dt. So, it is basically the two droplets come, a droplet comes and meets at the equator, right. So, that is the velocity with which this actually goes. Okay. So, this velocity is normal to the parent drop velocity. This drop is traveling like this, right. Okay. So, this particular thing now becomes that, right. So, as the droplet spits out, it spits out in those directions perpendicular. Now, it can happen in a plane anywhere around that perpendicular plane, right. So, if it is going like this, okay, the daughter droplet can come anywhere in this plane, all of these are perpendicular, right. Velocity magnitude is given, the plane is given, but exact direction is completely arbitrary. There is a certain randomness, because you can never predict exactly how it is actually happening, right. Okay. So, this actually gives you that what will be the velocity of the daughter droplet. Okay. This is once again this Cv is of the order 1. Now, there is a lot of empirical things about all this work, okay, as you can see, but it is just to give you an idea that this droplet is traveling, it just spits out the daughter droplets in the perpendicular directions, right, and that velocity is nothing but the velocity with which the deformation is actually moving. That means the two sides, the deformation is this, right, this is the velocity of these two sides, right, this is the velocity with which this front is actually moving, right, that velocity is taken out by the daughter droplets. Okay. So, the tab model also yields what we call the breakup time. Okay. We will not go into the math of that, right. So, the breakup time is right over there in front of you. Okay. So, as we said, it is valid for that Weber number range. Okay. So, the breakup time, as you can see, if you have a very low value of surface tension, right, if you have a low value of the surface tension, what will happen, and what happens when you actually have, let us say, a small droplet. So, that can be left more like a homework kind of an exercise, where you can kind of see and visualize, try to visualize yourself that what will happen to the breakup time, okay, what will happen to the total breakup time. Okay. Now, we already said a lot of things about droplet breakup, okay, and we said that what is the role of viscosity. Viscosity basically damps out the whole thing, but the breakup, as we saw from that chart by Jerry Faith, for a large value of Onsorge number, it is still dominated by the Weber number effect, okay, that is by surface tension essentially. Okay. The tab model can be further refined, okay, to take into account the tiny fragments which are produced by, that means the ligament like structures. Ligament structures are like this, right. So, they are non-spherical. So, that model is called enhanced tab model or ETAB. Okay. And there are other breakup models also, like droplet deformation breakup model DDB, cascade atomization, and droplet breakup model or CAB. But one of the more popular and for example, but these models all, these are very for low Weber number kind of a spectrum. For a higher Weber number case, you will always see that the droplets, if you look at this picture over here, there is always some degree of oscillations or periodicity within the droplet surface. Okay. So, there is some oscillation. So, it is basically a multi-mode oscillation, so to say, right. It is multi-mode oscillation, okay, and that usually happens on the surface, waviness on the surface. In this situation, people normally use what we call the wave model. So, wave model is basically what that is basically a Kelvin-Helmholtz instability type of a model. Is basically that, it Kelvin-Helmholtz instability type of a model, and it is comes through the linear stability analysis, okay, and that is how we get to the KH instability. So, this takes into, this is more sophisticated in a way, okay, because it can actually predict multi-mode kind of an oscillation on the droplet surface. So, it is very useful in primary breakup as well as in secondary breakup, because the droplets may not break up just by a simple vibration, one dimensional vibration, it is actually multi-modal vibration, so to say. Okay. So, if you just do a very quick recap of what we did earlier, that even the Kelvin-Helmholtz thing, if you look at, if you remember the first few lectures, what were they? There is that gravity is actually not there into the picture, right. So, there is an interface, sharp interface like this, what we have over here. There are two fluids which are moving with a velocity u1 and u2 with difference in density. Right now, we are not stated anything about liquid and vapor. I mean, of course, in this case it is, one is a liquid phase, one is the gas phase, okay. And what happens is that this interface undergoes a degree of small perturbations, okay. Now, that perturbations wavelength is given by lambda, and the wave number and the corresponding wave number is given by that. Whereas on the, so this is an infinitesimal perturbation of the interface, right. The idea is to see that if there is a perturbation on the interface, whether that perturbation grows or it decays, what happens, okay. If the perturbation, so if you look at back to the slide once again, you will find that the perturbation can be written in this particular form. That means the y is the amplitude basically with which this perturbation is actually growing. So, there is an n naught, and then there is an omega, there is this k, this k is the same as this k, right. Okay. Now, we consider only the real part of this, okay, the real part of this, okay, and the real part is that. Now, the real part of this omega, which is basically nothing but the growth rate of these perturbations, okay, if this omega is greater than 0, this waviness on the surface basically grows with time, it will grow like this, right. If however, this is less than 0, this will attenuate with time, okay. So, depending on whether the, so if you imagine this to be like a droplet or like a sheet or like a liquid sheet, right, okay, and you have all this waviness that are created on the surface, right. Some waves are going to be damped out immediately because of the effect of surface tension and other players, right. Some waves are going to grow, okay. So, this will become aggravated, right. As it becomes aggravated, these points will undergo breakup, right. So, you have an aggravated liquid sheet, right. So, it becomes like this, then in the next instance it becomes more violent, right. So, it will start to detach, right, the liquid will start to detach from the surface, correct. Okay. So, the idea is to basically use a stability analysis to see that what is the perturbation that you create on the surface of the sheet, right, which is a infinitesimal perturbation. This is the growth rate of those perturbations and this is the wavelength of that perturbation. The idea is to see that the real part of the perturbation, the real part of the growth rate, if that grows with time, then that means that perturbation will aggravate and become something like this, otherwise it will attenuate. So, there are some criteria space, not all wave numbers can grow, not all wavelengths can grow, some wavelengths will grow, some wavelengths will not grow, and that depends on the surface tension, a lot of other factors. Okay. So, in the next class what we are going to do, we are going to look at this Kelvin-Helmholtz instability. Okay. We have already done this earlier, right. We have to see that whether for a given lambda, whether this disturbance, how it grows, how it decays, and how we can apply it in a droplet scenario. I have already given you some idea that how it can be applied. So, we will see in the next class that how it is literally applied to basically in a droplet kind of a context, and that would be very important, because based on that we will wrap up this atomization part. There are more models, there are more complicated models, but these are the two basic models that you should know. Okay? Thank you.